Easy enough? Okay, so this gives us a basic framework for estimating species richness at equilibrium. There are a couple of quick points that are fairly obvious that I'd like to make. And the first is that species richness will be increased with higher immigration rates and higher rates of P, or higher numbers of species on our mainland source pool. So think about that graph we just put together, right? Think about our extinction and our immigration lines. If I increase that immigration line a bit, that will shift our little dot, our equilibrium dot, to the right, which means that species equilibrium is increased, or the number of species at equilibrium is increased. Think about your p-value here. If you move the p out further, so you increase the number of species that could come from that mainland, it also increases species richness. So go back to those graphs and test yourself out, just to make sure I haven't misspoke. Secondly, let me also say that extinction rates, as they climb, that results in a decrease in species richness at equilibrium. So again, if you move that extinction line up, you'll notice that the dot, right, our equilibrium dot, will move to the left relative to where it crosses the immigration line. So increased extinction rates will reduce the overall species richness we would expect at equilibrium. Now there's probably a third point that I think is really important to mention too, and that is that we're dealing with species richness, right? So we're estimating species richness at an equilibrium state. And so we're assuming that that number of species remains constant, relatively unchanged from one time period to the next. But the point is, even though that remains constant, we have a very different composition of communities over time. So just because we have the same number of species doesn't mean that the species there at any one time is the same from one time period to the next. So there's a lot of turnover. Why would we have turnover? Well, again, we've got all these species that are coming in as immigrants. They're arriving to the island. And then we also have residing species that are going extinct. So again, there's this turnover. If you're a biologist and you go to your island, in year one you'll see an assemblage of species. If you return another year, say 5 years down the line, you may have the same number of species, but the composition of species is different. And so this turnover is important, and we can estimate turnover rates, because turnover rates give us a means of estimating how many species we expect to persist or go extinct in a given time frame. So how do we estimate turnover rate? Right? How do we estimate it? It's estimated on the y-axis, and it's the number of species arriving or disappearing per unit of time at equilibrium. Remember here, we've got our equilibrium point, and that is the number of species we expect at equilibrium. That's what we derived before. That's where our extinction curve, our extinction line, and our immigration line cross. So what then is turnover rate? How do we express that graphically? Well, as I mentioned, it's determined by the y-axis here, and our turnover rate at equilibrium is essentially here. And we're going to call that T hat. So T is our turnover rate, and hat here gives us an indication that it's at equilibrium. So the turnover rate of species here at equilibrium is here. An important point to recognize is that as immigration rates increase, if our maximum immigration rate increased, that will do what now to our T hat value? That will increase our T hat value, right? So imagine taking this line and pushing it upwards, right? If we did that, that would raise our equilibrium point, and that would give us an increased rate in turnover, which sort of makes sense. With more immigrations, you've got more turnover. And the same would be true with extinctions. If we increase our extinction line, we would also expect our turnover rate to increase. So this is how you would sort of visualize it graphically. but how could we describe it mathematically? And that might have some value as well. To describe it mathematically, we're basically saying the turnover rate, the rate of turnover in species, is really relative to the amount of species that we have. Now the turnover rate could be either the turnover in extinctions or the turnover in immigrations, because we know that they're both balanced. They're basically the same at equilibrium. So the turnover here is really a function of, again, the number of species that we have. That would be our S hat value. That is essentially equivalent to our maximum immigration or maximum extinction rates, which is kind of like a measure of turnover, relative to the maximum number of species we could have on that island. So it's a little tricky to visualize, but it does set us up for mathematically describing turnover rate. So here we have T hat relative to S hat, turnover relative to species richness at equilibrium, being proportionally the same as maximum extinction rate relative to the number of species that occur on our source pool, or the maximum number of species that could occur on our island. So we can use this as a basis for solving T hat and coming up with a new way of estimating it mathematically. And to do that, we just simply cross-multiply with this equation. So we cross-multiply and we get Tp equals S hat E. And we can divide by P now, and that gives us S hat E divided by P. Now, as you recall from earlier, we did manage to figure out or generate a new equation for S hat. Remember what that equation is? So S hat is I times P divided by I plus E. Remember that one? So we can take this expression now and we can substitute it into the equation and then simplify using algebra the equation, and I'll let you do that on your own, but basically what it gives us now is the following. T hat is I times E divided by I plus E. So if we know something about I and we know something about E, we can mathematically calculate our turnover rate. So at this point we have the basics of the MacArthur-Wilson equilibrium model here. So immigration and extinctions then will allow us to make some statements, some predictions about species richness, as long as we know that there's a mainland out there somewhere and that mainland has a certain number of species that we also know. There are a couple of other important factors, and I mentioned these earlier, and those two factors include area and isolation, right? So the size of an island can impact species richness. The isolation, how far that island is removed or separated from a mainland area or another island, also has an impact, a potential impact on species richness. So we're going to fold these into our model here, and we'll start with area. And when we start with area, there are a couple of assumptions we have to make in order to really build this into the model. The first is that population sizes, so the population size of an individual species on an island, will be proportional to island size, right? So islands of different sizes will have the same density of individuals. So as islands get bigger, population sizes will proportionally get bigger as well. The second assumption that we have to make is that as population sizes get bigger, these larger populations are less susceptible to extinction than smaller populations. So larger populations are less likely to go extinct than smaller populations. Why might that be? Think about that for a moment. Why are smaller populations more susceptible to extinction than larger? One potential answer to that relates to some of the earlier material we've covered in other modules. So smaller populations can be more susceptible to random events, random processes, for example. Think about demographic stochasticity. That chance randomness acting on individuals has a more magnified effect on a smaller population and can cause that population to go extinct, whereas larger populations are much more buffered against demographic stochasticity and other kinds of processes. So if we had to wrap these two assumptions up into a single statement, population sizes get larger and extinction rates get lower for larger islands relative to smaller islands. Let's first have a look at the effect of area, and I've put a little A up here in the corner to point that out. So we've gone through a couple of assumptions, right? And we've assumed that area really affects extinction rates. And we're assuming it doesn't really have that much effect on immigration, right? Because area can change the nature of population sizes, and that can have an influence on extinctions, and it probably won't really affect the rate at which immigrants are reaching the island. Although we'll come back to that point rather a little bit later. So this is a graph that we've left off with, right? Should be familiar. This is a graph that shows our immigration and extinction lines. And of course we've got our S hat value here. So this is our species richness we expect at equilibrium. So if we incorporate this area effect, again we're assuming that extinction rates will be much lower on larger islands relative to smaller islands. So if this was our small island up here, we would expect extinction rates for larger islands to be lower. So they would be lower in terms of rate. And so let's draw a new line now that captures that effect. So here's our new line. And what do we see? Well, we see for larger islands now, we would expect an equilibrium point to be different. We would expect for larger islands our equilibrium point to shift to the right on our graph, which means we expect more species at equilibrium, a higher species richness on large islands relative to small islands. Here are two new equilibrium points. So that's the area effect. Let's now have a look at this effect of isolation, and I've put a little I up here to indicate we're dealing with isolation. So isolation again is how far removed, how distant our island is from our mainland source pool, our mainland area. How far is our island away from Honduras, right? So again, we've got the same graph here, and we're assuming now that immigration is really what's affected by isolation, not extinctions. And why would that be? Well, if you're a little insect, for example, and you're in Honduras, it's a lot easier for you to get or immigrate to an island that's nearby relative to an island that's quite far away. So an island that's 50 meters off the coast is pretty easy for you to immigrate to. The likelihood of you getting to an island that's several kilometers off the coast is very low. So we would expect then for faraway islands immigration rates to be lower. So if this is our immigration rate for nearby islands, for faraway islands, our immigration rate would be lower. So let's draw our initial equilibrium, our S hat here, our species richness at equilibrium. And let's draw a new line now that captures this isolation effect. Yes. Okay. So what's happened? What we see now is that for faraway islands, our S hat, our species richness now, changes. So our equilibrium point shifts to the left. And so our S hat for faraway islands is less than our S hat for nearby islands. In other words, those islands that are far away will have less species richness than those islands that are nearby. Does that make sense? So in summary, the equilibrium model indicates that species richness is really a function of immigration rates and extinction rates. And not only that, the physical characteristics of an island can influence those two factors. So area can have an influence on extinction, and isolation can have an influence on immigration. So we can estimate richness as well as turnover rates at equilibrium by looking at our graphs and figuring out where our immigration and extinction points cross. So that's the basic equilibrium model. At this point, I'm going to pass you over to Terry, who will build this model and explore it a bit more in a spreadsheet. So Terry, on to you.